Yeah, good afternoon. I'll start by thanking the organizers for organizing such a wonderful event and giving me the chance to speak here. And the title of my talk is What's New in Moonshine? And it's based on joint work with a list of wonderful collaborators and by many others. So a lot is new in Moonshine, both on the mathematical front as well as on the physical front, and both at the technical level as well as at the conceptual level. So in order to make sense of these news headlines, what we have to do is we have to spend some time to put it in context by reviewing the old news. In the second part of my talk, I will review some progress in understanding UMBRAL moonshine in the relation to K3 string theory. And in the third part, I will briefly discuss how many new moonshine cases are being discovered. So the old news. In 73, that's very old, a finite simple group of monstrous size was suspected to exist. And its character table was computed in 78. And shortly after, it was realized that it has a bizarre relation to a canonical modular function called the J function. So it is a function on the upper plane with the property that it's invariant under SO2Z generated by T and S transformation. And if we look at the Q expansion near the I infinity cusp, then we see that its Fourier coefficients can be expressed in terms of dimensions of irreducible representations of this monstrous group, these numbers in red. To get an understanding of these representations, we also want to know something about the characters and not just the dimensions of the representation. And that led to the famous Monstrous Moonshine conjecture, which states the existence of an infinite sequence of monster representations, so one for each powers of Q, such that when you compute its group characters graded by the corresponding powers of Z, of Q, then you get an infinite Q series that has the property that, first of all, it's invariant under a subgroup we call gamma sub G of SO2R, and secondly, and it has the expansion with this two initial term when you expand it in Q, and these two conditions are in fact enough to fix this function uniquely. And the reason lies in the fact that the fundamental domain of this subgroup gamma sub G of SO2R is basically a sphere with a few points removed. And what we know that if we need to specify an isomorphism between two spheres, in this case given by the function J, we just need to specify 3 points. So that's why this function is unique. So what's the representations? In 84, Franco, Lebowski, and Merman constructed this infinite sequence of representation by taking a C equals 24 chiral CFT, basically given just by 24 free bosons on a specific torus given by the Leach lattice. So what is that? So some even older news was that in 73, Niemeyer has proven the theorem that there are just 24 even self-dual lattices with a definite signature in 24 dimensions. So one of them is the Leach lattice that's singled out by the condition that there's no root vectors in the lattice. So root vectors are the shortest vectors allowed by the evenness condition. And there's other 23 that have a non-trivial root systems given by the combinations of ADE root systems, and moreover, the root systems is enough to specify the lattice. So the construction of the chiral CFT was verified by Borcherds in 92 using string theory elements. And this Borcherds proof has been further illuminated very recently by the work by these three persons in terms of heterotic strings compactified down to 1 plus 0 dimension, and their construction also shed some light on the famous genus zero property of the monstrous moonshine. So we have two continents, one that's the continent of finite groups and the other continent of modular objects. And thanks to Monstrous Moonshine, there started to have traffic between the two. And in this case, the vehicle was given by this chiral CFT. V natural is its name. And in a related development, it was also realized that we can also have a moonshine for the so-called Conway zero group, which is the symmetry group of the Leech lattice, also connected to the general modular functions. And the vehicle here is a supersymmetric version of a chiral CFT. We call it the V supernatural. So after quite a bit of silence, it was realized in 2010 that K3 elliptic genus also hides moonshine in it. So recall that the nonlinear sigma model on this Calabi-Yau twofold is a conformal field theory with 4,4 supersymmetry. And the elliptic genus, defined in this way, then computes the BPS spectrum and is invariant when you vary the moduli of the theory. And when you decompose it into n equals 4 characters, we obtain a very nice infinite Q series. We call it H of tau here. And then if you look at the Fourier coefficients, you might realize that, again, it's connected to the dimensions of irreducible representations of another sporadic group. This time, it's the sporadic group M24. Moreover, this infinite Q series also has the property that it's an example of the so-called Mach modular form. Namely, you can trade holomorphicity with modularity in a very controlled way by adding a non-holomorphic integral of something that's called a shadow function. And 3 years later, UMBRAL moonshine was found to be a natural generalization of the MATHIEU moonshine. So the construction of UMBRAL moonshine takes each of the 23 NEMA lattices with a root system, and then on the one hand, the lattice symmetry will define for you a finite group we call it G of X, and on the other hand, we have the root system will determine some kind of modularity condition. And just like before, this modularity condition together with the expansion of the first term, the pole behavior at Q goes to 0, then uniquely determines for you a vector of Mach modular forms. And it's a generalization in the sense that if you take the special case where the root system is just given by a bunch of A1s, then the group and the Mach modular form you obtain is exactly the case that has been observed in the K3 elliptic genus. So just like before, it's not enough to look at just the dimensions of representations. You also want to look at the graded characters. So you can generalize this construction to build a vector of Mach modular form for each element of the finite group that you get from lattice symmetries. And then the UMBRAL moonshine conjecture then states that there exists some infinite sequence of representations for this finite group Gx, such that when you take the characters graded by the powers of Q, the infinite Q series you get coincides with nothing but the vector of Mach modular forms that you obtain. So because of UMBRAL moonshine, you see that it seems that there should be more traffic between the two continents. However, in this case, we only have the dashed lines because we don't know yet what this infinite sequence of representations should be. So this will be the topic of the second part of my talk. So to know how to think about how to construct these representations, then the first thing you might want to do is you want to put this moonshine in this kind of physical context. And for the case of M24 moonshine, the physical context was initially given to us as given related to the elliptic genus of K3. And in 2014, we proposed that not just that case, but actually all 23 cases of UMBRAL moonshine can be related to the sigma models of K3. So the main motivation was the mathematical fact that the uniform construction of 23 cases of UMBRAL moonshine can be translated into a uniform way to split the elliptic genus of K3 into two parts. The first part is given by the elliptic genus of the 8E singularities corresponding to the 8E root systems of the lattice. And the second part is given by the contribution of the Mach modular forms. And this vector of Mach modular forms can be conveniently repackaged into one single function with one extra variable. And then you can show that this equation is true in all 23 cases. So once you're given such a construction, then it's very tempting to twine these constructions to get the corresponding twining function. So what do I mean by that? If you have a finite group symmetry generated by a group element G in your theory, then when you compute the partition function, you can also insert this group element G in your trace over the Hilbert space. In that way, you define the so-called twined partition function, or in this case, the twined elliptic genus. And because we know how the finite group acts on the roots of the lattices, we also know how it acts on the corresponding AD singularity theories. So it's a straightforward task to write down the corresponding twined elliptic genus of the theory. And the second part is also straightforward. We simply just replace the Mach modular form by what Monstrous Moonshine dictates. Combining the two terms, we again get a very nice function, which might play the role of knowing something about the elliptic genus of K3 twined by its physical symmetries. However, we note that this whole construction uses no physical input whatsoever so far. So far, we only use the input of Monstrous Moonshine. So we want to know on the physical side how it compares. So first, we want to know the question. We want to ask the question. So what are the symmetry groups of K3 sigma models? So to be more precise, when you go from point to point in the moduli space, then the symmetry group of the theory changes. So the question I want to ask is, given a finite group abstractly defined in terms of generators and relations, is there a point in the moduli space of K3 sigma models such that the theory has a symmetry group that's isomorphic to that abstract group? And the question was answered by this very nice work. And it says that what I said is true if and only if this finite group G satisfies the following two conditions. First, it is a subgroup of Conway 0, the symmetry group of Leech lattice. And secondly, because the group acts on the Leech lattice and hence the underlying 24-dimensional space, we require that the group fixes pointwise at least a 4-dimensional subspace of that 24-dimensional space. And if that's true, then all these groups can be realized as a symmetry group somewhere, and vice versa. So it appears that the Conway group is really the natural structure that organizes the symmetries of sigma models of K3. And remember that we also had the Conway Moonshine available, so this consideration has led to the following very nice construction. So the idea is the following. You have the V supernatural, this chiral supersymmetry, the super conformal field theory. And then you take 4 of the 24 fermions available in the theory, and then you build U1 currents from it. And then with that U1 current, you can then add the fugacity related to the corresponding to the U1 charges and compute the partition function. You get a 2-variable function. And that turns out to be nothing else but the elliptic genus of K3. And at the same time, because of this, you have to fix these U1 currents, this extra structure breaks the symmetry from Conway group down to subgroups preserving a 4-dimensional space. So you get a nice result that for each one of these four-space preserving subgroup of Conway group that are relevant for the physics of sigma model, you can compute a twined partition function of this chiral CFT V supernatural. And again, you want to compare with the physics output of the sigma model. So to compare that, we also have to remember that two groups are isomorphic to each other. Does not mean that they act in the same way on two theories at two different points in the moduli space. So physically speaking, the relevant equivalence relation is given by conjugacy classes by the T-duality group. So that's why in the work of last year, we classify such conjugacy classes, and we concluded that there are at most 81 different twining elliptic genus that you can get at each point of the moduli space of the sigma model. Why at most? Because in principle there could be accidental coincidence. So another interesting data point is 56 different twined elliptic genus has been computed using specific models of K3 sigma models at specific points in the moduli space, for instance, the orbifold points. And that also includes using the UV London-Ginsburg orbifold description. And finally, collecting functions that's given by UMBRAL moonshine and Conway moonshine, we obtain 69 distinct twining functions that uses just the moonshine observation. Okay? And then after doing some sanity check and with some blind trust in the power of moonshine, in this paper we conjectured that these 69 functions all appear, and they are all there are. So the statement is, given any one of these 69 twining functions that moonshine gives us, and there exists a point in the moduli space such that the theory has the appropriate symmetry. Moreover, when you compute the twined elliptic genus, it coincides with this one of the 69 functions. And the other way around, given any point of the moduli space, compute any twined elliptic genus that you can compute there, it has to coincide with one of these 69. So impressively, this conjecture was actually proven this year by these three people using considerations from wall crossing of black hole states in 4 dimensions. However, this is not the whole part of the story, because not all 23 of the UMBRAL groups are subgroups of Conway that preserve a full space. For instance, M24 is not one of them. That tells you that there's a part of this symmetry group that just cannot be compared to with the sigma model symmetries. And this forms a hurdle towards constructing the actual representations underlying the 23 cases of UMBRAL moonshine, although their existence have all been mathematically proven. Despite of this hurdle, there has been progress. Namely, as far as I know, 8 out of the 23 cases of UMBRAL moonshine have been solved in the sense that we can have a construction of the explicit representations that appear. Notice, however, that we cannot claim that we have solved 1/3 of the problem, because if you look at the groups, and in the third column, I also gave the dimensions of the biggest representation, and they're all pretty small. So in this, we're solving basically the smallest cases of UMBRAL moonshine. But however, in this case, these are very encouraging signs that many of them are being solved. So let's take a very quick look at how they're solved. So in the first case, the main ingredient is an identity equating the Mach modular form with an infinite lattice sum, and you just let the group to act on the lattice in a straightforward way. And in the second group of the examples, what you do is that you cook up some chiral CFTs with fermionic and bosonic ghosts, and its partition function typically takes an infinite product form like this. And they are perfectly modular and nice functions. However, they do have poles on the z-plane. For instance, you can see that this function has a pole when you take y equals to q. Then the relation to the Mach modular forms we want lie in the fact that there's a mathematically well-defined canonical procedure to remove these poles from this function. And the remaining part is exactly than the two-variable function that encodes all the information about the Mach modular form. So using this method, another group can be solved. And the third example, well, the group is quite a bit bigger, and moreover, it is not one of the Conway subgroups that preserve a 4 space. However, we can build a CFT with fermionic and bosonic ghosts and free fermions, and we take some orbitals, and with this CFT, we managed to obtain the corresponding twinned elliptic genus of K3, and that solves the problem. So also notice that this is really, so far, the first example that really make use of the connection to K3. So to summarize this part, for some mysterious reasons, we do not comprehend yet the problem of moonshine and the problem of stringy K3 symmetry seem to be somehow the same question. However, we still haven't found the correct vehicle that takes us between 2 countries in the 2 continents. And different groups are trying out different ideas. And this is, I hope, later that we will hear something about very soon. So in the third part of my talk, I'll show you how some new examples of moonshine are appearing recently. So this is a short list of them. So there's Thompson group being involved, and the Onan group, which is very nice because it's a so-called paria group, which means that it has nothing to do with the monster family. And in the third example, it involves functions that coming out related to M5 branes, and there are many new examples brewing. And then, let's take a look at the third class of examples. So the physical setup is an M5 brane wrapping a divisor in the Calabi-Yau. One way to describe it is in terms of an effective string called the MSW string, which is a 0,4 super conformal field theory. So we can define and generalized elliptic genus. It's slightly generalized from the definition before because we inserted some fermionic, we inserted some F squared insertion to soak up the fermionic zero modes, and we skipped the contribution from the non-compact momentum. And so the first example involving wrapping 2 M5 branes on P2. So famously, this can also be described by a topologically twisted n equals 4 Yang-Mills that was studied by Waffa and Witten in '94. And its partition function that famously involved the so-called Hurwitz class numbers. So these are numbers that count the SO2Z in equivalent classes of quadratic forms with discriminant D. So remember that the quadratic form that looks like ax squared plus bxy plus c squared, cy squared has the discriminant that's given by b squared minus 4ac. And this generating function of the Hurwitz class number is in fact a Mach modular form. And in some unpublished work, we show that when you rescale this function by a factor of 48 to get integral coefficients, then what you get is a function that encodes M23 moonshine. So there's yet another example. So when we wrap a single M5 brane on the petal 9, or so-called half K3, and this is also very interesting because it's the so-called E string, and the partition function is controlled by a certain modular form, and we show that it encodes M11 moonshine. So you might ask yourself why all of a sudden there are so many new examples. I want to point out that these new examples are really quite different from the old examples in the following 2 very crucial ways. First, now the group representations are allowed to have signs. Namely, for each powers of Q, you have a representation that has an even part and the odd part. And the coefficients of your Q series of your modular form is then given by the difference between the group characters of the even part and the odd part. So this mimics, for instance, when we have the bosons and fermions and so on. But this leads to a lot of cancellation, so it's harder and harder to see with naked eyes which groups that should be involved. And second important difference is that the functions are no longer determined uniquely by modularity condition and the pole structure. So remember that in, for instance, Monstrous Moonshine and UMBRAL Moonshine, it was very nice because, you know, the functions are uniquely determined by these functions, so that gives, let's say, the sort of a predictive power of Moonshine. But now we have given this up, so these functions live in the space where other cusp forms also live, so it means there are functions you can add and subtract without changing any of these conditions. So it is really, in some sense, a slightly different game from before. So let's conclude. And we have seen that there's the conclusion of this part is we have seen that there are quite a few connections. But they're all dashed lines because we don't know what is the correct vehicle that should replace our good old Cairo CFTs to give us the representations that we want. And it seems like there are many, it's quite flexible, the structure. We can find new examples. So we don't know what the landscape of this connection is. And it will be really helpful if physicists can put these connections more into a physical context, and that will very much help the exploration. So who knows, maybe the two continents is in fact turn out to be one, and we can just walk instead of flying or with a boat. But what is clear is that the new age of exploration is just starting. And with that, I thank you for your attention.
In the last part of the talk, when you discussed the M5 branes, you used two M5 branes to wrap CP2, whereas the slide after it was a single M5 brane wrapping one half. Why is it important to have a single M5 brane here and two M5 branes on CP2? What happens if you just take a single M5 on CP2?
Well, yeah, that's a very good question. So, in fact, there are like a large zoo of such examples that come out of M5 brane constructions, and you can look at them all. And in our work, we just look at a small number of them and notice that you can cook up some moonshine for them. So, I mean, I think it will be very interesting to explore these other functions.